So now we move to another topic that I call root finding techniques. Root finding techniques. So there is no argument about it. If you are going to be an engineering student or you are going to practice engineering, you have to find some roots. You get to a point that you need to find roots as part of getting solution to a problem. So there are different ways of getting the roots of a problem. One of it is the graphical method. Like you have seen in the just concluded lecture, at a point in time we had to find the roots of polynomial graphically. So graphical method is one of the ways you can get the root of a problem. So if you are doing that, you want to look at where does the plot crosses the y-axis when it is 0, when y is equal to 0, when does the line crosses it. That's where you get your roots if you are working graphically. Okay? Then you could use numerical techniques to get your roots. So here are some of the numerical techniques that you can use. One of it is called the Newton-Raphson's method. So if you are using the Newton-Raphson method, you are trying to iterate to refine the value of your x. X now is the root. So you are trying to refine it until you get the best value for your root. So how do you refine it? So we say x subscript n plus 1 is the refined root. And that x is equal to a previous value that you have guessed before to be your root. In this case is xn. And we are subtracting from it f of xn divided by f prime of xn. What does that mean? F of xn means we have a function that depends on x, okay? And the value we are looking at this point when we say f of xn is the value of that function when your x is equal to xn. You know, x could be any value, but at this time we are focusing on what is the value of that function when our x is equal to xn. Then what is f prime? Is the first derivative. So what's the value of that first derivative when the value of x equals to xn? So you continue to iterate until you get to that value of x that it is best based on the prescription that you are given. Another method, numerical method you could use is the second method. The second method, the equation is as displayed above. So it's also iterative. You are refining the value of your x until you get the best x. So the formula is as displayed in the box. So this time around, you are not looking for a derivative. Everything is based on the function, but the function has been evaluated at different points. So the function has been evaluated when x equals to xn and when x equals to xn minus 1. Okay, those are the points where your function has been evaluated. So this time around, you don't need to evaluate your first derivative. Okay, so what does this mean? For the first one, I did said we made a guess that we are trying to fine tune. Our guess was xn. But for the second approach, you will need two guesses, because what I'm refining is what is on the left hand side. So the guesses and the function based on those guesses are on the right hand side. So the guesses are xn minus 1 and xn. So what does that mean? Xn minus 1, in terms of order, n minus 1 comes before n. Okay? After n minus 1, we have xn, right? Then we can have xn plus 1. So if I call my first guess x0, then it makes sense to call my second guess x1. Then the first refined value, it makes sense to call it x2. So that's how it works. Then we also have the bisection method. Bisection method. So what does it require? So you have a function and you are evaluating that function between an interval. Okay? between an interval. So the interval here is a and b. So you are speculating that the root of that function is between the interval a and b. So how do we now get the roots if you are using bisection method? So before you can say this thing even has roots lying between this interval, it means that the function of a, if you multiply, this is a function now, you put a, you have a function f of x, so you put a inside f of x, you get a value. You put b inside f of x, you get a value. So those functions f of a, f of b, by the time you multiply it together, it has to be lesser than 0. Okay, so if the value is lesser than 0, that means it's negative, right? Okay, then you can say, okay, there is a root in between this interval. So if the sign is not negative, fa multiplied by f of b is not negative, then you know that that interval does not make sense enough. You can't get any root out of it, so there's no point going ahead with the rest of the process. So let's assume now is negative. What that means is that the sign of f of a is different from the sign of f of b, right? For f of a times f of b to be negative, that means the sign of f of a and f of b are different. Okay, so once it's different, the next thing is that you want to find what is the midpoint between a and b. So that's why you see the midpoint, which is c, is equal to a plus b divided by 2. So you want to locate the midpoint. So what do we do with the midpoint? So once you get the midpoint, you now evaluate the function again using that midpoint. So if you evaluate the function again using that midpoint, if the value you get is 0, then c is a root. That c value is a root. But if it's not equals to 0, then that means you are not done with your search. You are still searching for the root. So what do? The next thing is that you want to look for that interval where the root can lie. Okay? So you have point C now. So what you need to do is that you multiply, you started with A and B. So now what you are going to do is that you multiply f of A by f of C. If the value is negative, then you know that your root is going to lie between the interval A and C. If it's not negative, you discard that interval. Then you move on to f of B times f of C. Okay? If f of B times f of C is negative, then you know that your root is going to lie between C, B and C. So the next is that whichever it is, either A to C or B to C, the next is to find what? The midpoint. Again, you need to find the midpoint of that. So when you find the midpoint, that value that you get, you put it inside the function to get the function at that point in time. So if the value is equal to 0, then you know that, okay, this new midpoint is the root, right? So if it's not equals to 0, then you continue the process as you have done. So you continue to have it until you get the root. But for this kind of method, it's not very likely that you are going to get 0 exactly. So what normally you will have is that you have a very small value, which is a tolerance limit that is very close enough to 0. Say something like 10 raised to the power minus 5. That's really close to 0. Anyways, depending on the project you are doing. But you may not get 0 exactly, but you might want to work with a tolerance limit. So once your f of C is close enough, is lesser than that tolerance value, then it's okay. This is the point. The point that gives me that that f of whatsoever f of midpoint that is close enough to 0. That is the root. Okay. Or you continue the iteration such that the interval, you know, you have one interval here, one point here, which is the interval. So as you are halving it, you know it's going close to 0. So once you have halved it to the extent that what we are left now as interval is even lesser than the tolerance limit that we are giving, then you stop and call that your root. So that's how bisection comes in. So you see that I have said something like, while the interval is still larger than the tolerance limit, you can still continue if you have not found what you are looking at. Then I have used if this is greater than this, if this is greater than this. So those are conditionals for those of you that actually did the training that I asked you to do. So you should by now be familiar with conditionals. Okay, so that means if you want to use this technique, if you really want to enjoy using this technique, you might want to loop it. You might want to use some conditionals while solving this. So we will come back to this later if the calendar permits. So let's move on to other method of root finding. So one of it is you could use the zero function that is built in Matlab. So Matlab has a built-in function called F0. So you can use that to get your solution. So F0 has been constructed in a way that it combines different methods that I have mentioned, or which I may not even mention, to get an efficient root. To get your root efficiently. So one of the methods that has used is the bisection and the second method. So you have factored various things in so that the root that you are getting is effectively gotten. Then another thing is, if you are working with polynomials and you want to find the root of polynomials, you could use roots. This one has ROOTS function to get the root of polynomials. So the difference is that, fine, this is also built-in function, but root is majorly for polynomials, anything that has degree from 2 and above. But for F0, it could be roots, it could be polynomial, it might not be polynomials. It could be anything that you need to find the root. So a limitation of roots is that this is just specialized for polynomials. So let's try and solve some problems before we close for today. So this is a question, a very simple question. The idea is for you to know how to use different techniques in finding roots. It's not how complex the problem is. It's still the same principle that you use for a similarly simple equation that you will use for any other complex situation. So we have this function f of x equals to s cubed minus 3x minus 5. So we are asked to find the number of iterations that we need for you to have a solution. How do you know that you have found a solution? So they have provided for you a tolerance limit. So once the difference between the previous value of x and the current value of x, once difference is not greater than the tolerance limit, then you say, okay, it has converged to a solution. Okay, so this time around, since we have not moved into programming in Matlab, we have not officially talked about conditionals and all of that, all of the loops that you can look at. So we'll be doing it, let me call it manually. So once we compute one value of x, we will use arrow key to fetch the next one until our result has converged into a solution. Ordinarily, we can do it better than that, but we are building one step at a time. So what we are focusing now is knowing how to use different techniques to find roots. Okay, so now let's begin to solve. So I told you about the Newton-Raphson's method before, right? So the first solution, you have been advised to use Newton-Raphson's method, and for you to determine how many iterations gave you the converged solution. So I brought forward the Newton-Raphson method here. The Newton-Raphson method says the refined value of x is equal to the previous value, the one that you guessed, minus the function with respect to your guessed value divided by the first derivative of that function based on your guessed value. Okay, so that is what we are doing. So we are going to be repeating these steps until we have met the tolerance limit. So what's the first thing? We need to get our function first, right? So what is our function? So our function is what? F of x is equal to s cubed minus 3x minus 5. So this is what I've written here. F is equal to x carry 3 minus 3 accelerate x minus 5. That's the way you understand it. But I won't use this approach. It's very correct, but I just want to do something different. So I want to say f of x, the normal f of x I used to say. So I will say f of x. So this is the way Matlab understand f of x. F equals to at x inside parentheses. So that's the way to say f of x in Matlab. So what does it equal to? Leave some space. So it's equal to what? X raised to power 3 minus 3 times x minus 5. Okay, let me put a semicolon. So you see at the workspace it has created that function for me. So what else do I need? I need my f prime, the first derivative. So let me call my f prime f underscore prime, and that is equal to, so what's our f prime based on this equation? Okay, but before that I want to say f prime is also a function of x, right? So at x, so f prime is a function of x. So now can you give me what f prime is ordinarily? Is what? F prime, okay, yeah, 3 x raised to power 2. Okay, what's the next thing? Minus 3. So this is your work. You need to be able to find f prime by yourself, first derivative, so that you can supply what it is to Matlab. Okay, so now I have my f of x and f prime of x. So what do I need to do? What else do I need? I need my initial guess. Do I? So I need my initial guess. My initial guess is x equals to what? According to the question. X equals to 3. Let me put a semicolon. So with that, I can now compute a refined value for x based on the Newton-Raphson's method. Okay, so how do I do that? Now supply my formula for Newton-Raphson. So I want to refine x, so I can say x, the new x that I'm refining, the value, equals to what? What's it equal to based on that formula? Now, if you recollect when we started the preliminary class, we said, well, we can compute a new value for a variable from what it was before. So that's one of the reasons why we store values inside a variable, so that we can call it back and use it to do whatsoever we want to do. So x equals to x. So that means I'm saying my new x is equal to what it was before, okay, minus what? F of x, yeah, slash f prime. That was what we named it, right? F prime of x. Let's see if it works. So I'm not going to suppress it because actually we want to be comparing the values to know if we have converted to a solution. So this is our first iteration. Let's see the outcome by pressing enter. Okay. So the refined value for the first iteration is 2.45, 8333, and all of that. So if you compare the first value, which is 3, our initial guess, if you take the difference of the two, would you have something lesser than or equal to the tolerance limit? The tolerance limit is 1 times 10 raised power minus 5. You don't need a calculator for that, obviously you know. Because what is 1 times 10 raised power minus 5? 0.000, maybe 4 zeros before 1 after the decimal. So obviously this cannot give you, because you will not have anything less than close to 0.5 as your result here. Okay, so there are some things when you go for aptitude tests, for some of you that will apply for a job by yourself, aptitude test does not give you time sometimes to do unnecessary. There are something that once you cite it, you know the answer. You don't need to be okay. So that does not work. So we need to refine it again. We need to refine this value. So that means this value of x is going to be our new guess again. So instead of using instead of using 3, this will now be the guess now. And with that guess, we want to get a new value of, okay. So we get the formula again using the up arrow. Okay. So this formula still works. So we want to compute another value of x, and this is the current value of x now, what we just got. I hope you understand how it's working. Okay. So press enter. So that's the new value. So if you compare this value and this value, it will not give you 10 raised power minus 5. No need for calculator. So you continue the process. Okay. It's looking better, but this thing will not give you 10 raised power minus 5. Okay, so if you look at this, you might want to use your calculator on this, because it's now getting closer to what it can be. So anybody trying to get that for us? So let me do it one more time. So now if you look at the last value I got, you see that after the decimal place, 1, 2, 3, 4, 5, 6 digits after the decimal place is the same thing with the previous one. So I believe at this point the difference should be lesser than 1 times 10 raised power minus 5. Okay, I hope you get the logic. Okay, but you can use your calculator to do that. So how many iterations did we do? How many iterations did we do? So this was the first iteration, this is the second iteration, this is the third, this is the fourth, this is the fifth. So we did 5 iterations to meet up with the tolerance limit. Okay, so these are the solutions in case you want to work on your own, so that can be a confirmation or a guidance to you. So now let's solve the same problem using the second method. So it's still the same function that we are working with. But now the approach is different. The approach is what I have inked in red font. One of the differences is that we are going to be having two guesses to use the second method. So the guesses are 1 and 3. So x0 is 1, x1 is 3. So what we are looking for is our x2. The refined value is our x2. So based on this formula, we will say that our x2 is equal to what? Based on the formula on the board, x2 is equal to what? The formula says xn plus 1 is equal to xn, and so on and so forth. So we said the first guess is x0, the second guess is x1. The refined value, which is xn plus 1, is x2. So based on that, x2 is equal to what? So x2 is equal to x1 minus f of x1 into x1 minus, so what's this? x0 divided by what? x1 minus x0. So that's the method here. This is the second method. So that's what I've interpreted here. Okay. Then here we only need the function. We don't need the derivative. So what we are looking at is, with the first guess of 0 and second guess of 3, how many iterations do we need to do using the second method? That's what we want to see. How many iterations do you need to do before you get to meet the tolerance limit? So let me clear what we have before. Okay, so what's the first thing we need to do? Let's have our function, right? So it's easier to use the approach that I used initially to define a function instead of typing that equation often and often where it needs to appear. So once we use the function, the defined function, what we'll be left with is just to provide what is the values that will go in, instead of typing a whole lot of equation too many times. So we have the function. So the next thing, based on the equation that we have here, is that we have the function. Then the next thing is to provide the guesses. The guesses are xn minus 1 and xn. In this case, we call it x0 and x1. Okay, so our x0 so since we have defined that function, it recognizes our x anytime we need it. Okay, so we have the initial guesses. So now we should type the second function and use it iteratively. In this case, how we are using it iteratively is to fetch it again and run it again. Fetch it, run it, fetch it, run it until it converges. So that's how we are doing it iteratively. Even though I've said that there is a better way of doing that. So now let's type in our second function. So our second method says x2, that's what we are looking at now, is equal to what? X1, I've explained that before, minus f of x1, okay, multiplied by x1 minus x0 divided by f of x1, excuse me, minus f of x0. Okay, so that's it. So I won't need to suppress it because we will be comparing with what we had before. So let me press enter and see if you have a solution. Okay, so the first refined value says x is equal to 1.7. If you remove 1.7 from 3, which is x1, so you know you'll be comparing x2 and x1. So if you remove 1.7 from 3, that's not going to meet the tolerance limit. So that means you are not done. So for the second method, we need two guesses: x1, x1, x0. So what we need to do is that the previous x0 will go away. Okay, so we need to create another x0, and that x0 is going to equal to what x1 was before. Okay, and x1 now is going to be x2 that we just computed. Then we now need to calculate the new x2 by the second method. So that's what makes it iterative. So what am I saying? We need x0, and this time around is equal to what x1 was. Okay, so that's where to assign it. That x0 is going to be on your left hand side, and the value you want to give to it is going to be on the right hand side. Okay, then your x1 is now equal to the x2 that we just got. So now we can now get our x2 using the iterative method. This time around is the second method. So we had the formula before, we don't need to type it again. So we just fetch it. So this is it here. So it's going to do the computation based on the new x1 and x0 that we have specified just now. So that's the value. So if you compare 1.7 and 2.07, it's not near the tolerance limit. Okay, so what we need to do, we will set x0 to x1. We set x1 to the current x2, then we do x2 computation iteratively. Okay, it's still not close enough, right? So we continue the process until we see that we are close enough to it. All right. Okay. Is it close? It's getting closer, right? So that means it's converging to a solution already. So let's continue. So let's look at this. Yeah, it's getting closer. So anyone checking for us if we had gotten to where we need to get to? So if you use your calculator, I think it should be close enough to what is expected. So for this case, it was 7 iterations that gave us the results. Let me check again. It should be 7. So this was the first iteration, second, third, fourth, fifth, sixth, seventh. Yeah, 7 iterations. So let's use on the same equation, let's use the F0 function, which is built in Matlab. It's a built-in function in Matlab. So what that just requires is that you define your function just as we have been defining it before. So once you define it, you call the F0 function, this F0 function, and what are the arguments you pass into it? That function that you have created, okay, followed by your initial guess. This also requires initial guess, okay. This time around is 1 initial guess, just like the Newton-Raphson method that required 1 initial guess. So this requires initial guess. So you call the F0 function, pass in the function that you want to get the root and your initial guess. Then it's going to give you the roots. Let me clear this. Since the function is the same, let us just get it instead of typing it again. You will be practicing how to type it on your own during your study time. So this is the function. So let's say x0 initial guess equals to 3. That's our initial guess. So let's study the outcome. The outcome of this root finding. Let's study it in a variable called root. You can call it any convenient name. But like we said, it's good practice to use a name that is reasonable, that can help you remember what this thing does. So we say root is equal to, we call the function f0, open the parentheses, pass in the function. Our function here is f, okay? F followed by a comma, followed by our initial guess. So since we have stored the value of our initial guess inside x0, so we bring in x0, okay? So let's see if we have an outcome. So it's saying the root is equal to what? 2.279018 blah blah blah. You see, it's close to the values that we have obtained using the Newton-Raphson's method and the second method. Okay. And this is fast. So luckily for us, the example we are using is a polynomial. The method that we have used before, you can use it even if the function you are handling is not a polynomial. But if you are handling a polynomial, there is a plus that you could have used the function roots. So when you use the function roots, you are going to get all of the roots that has, because the function you are working with is cubic. So you expect that it should have 3 roots. But all of the things that we have been getting has been 1 root. But with the roots function, you can get all of the roots that equation has if you are working with a polynomial. So let's use the root function. If you are going to be using the root function, the first thing is that you should create a vector that has the coefficients of all the powers that are in your polynomial. Okay? So once you create a variable, which is a vector that contains the coefficient of all of the powers in that your function, then it is that vector that you are going to pass inside the function roots. It's not complicated, just as easy as f0 function. So what's the first thing? We want to create a vector that has the coefficient of all of the degrees inside the polynomial. So let's call it p. Let me clear this up again so that the screen is clear enough for you to follow. So we want to call it p. You can call it any name. Okay, so we have the function we are working with is what? What's the function? S cubed minus 3x minus 5. That is the function that we have been finding its roots all along using different approach. So we start with the highest power in that polynomial. What's the highest power in this polynomial? The highest polynomial is 3. So what's the coefficient of that highest polynomial here? 1. So that means 1 comes first. So the highest order is 3. So we move to the next power. What's the next power? Okay, so what's the coefficient of power 2 in this? Is what? 0. You should let it know it's 0. Okay, because it's trying to interpret the function you are working with. So if you don't put 0 and you move to the next one, it's going to interpret it differently. It's going to be thinking maybe this is a quadratic function. Okay. So what's the next order? 1. X raised to power 1. So what's the coefficient? Minus 3. So what's the next order? 0. So what's the coefficient? Minus 5. So you have created the vector. So now you are good to go. Now that you have created the vector, you can now pass it into the function roots. So let's say the solution you are looking to get, you want to store it in small letter r, and the function you are calling to get the solution is roots into brackets that coefficient that you just created. Okay, so I don't want to suppress it, I want to see my answer. So let me press enter. So those are the results. It could be any power. There is no limit to the power, but just make sure that you pass in the coefficient of all of the powers inside that equation correctly without missing anyone out. So if you look at the solution, we see that the first one is a real number, okay, because the complex part, the imaginary part, is all 0, and that value is very close to what we have gotten with the first 3 methods. Now the other 2 results, they are what? They are complex numbers because they have values for the imaginary part. Okay, so that's that. So as a plus, let's just plot. Let's find the solution graphically. I know we've done something like this before, but just to establish that all of these approaches are actually valid. So let me clear the screen. Okay. So now, if you want to find a solution graphically, so we have maybe our y data set against our x data. For example, this function, if you want to find the solution, we have range of value of x, right? When we have range of value of x, then we are going to compute our y values based on the function that we are given. So when we make a plot of y versus x, we determine the roots at the points that the the curve crosses the line when y equals to 0. We have said it today, and we have done something like that before. So what I'm repeating is that we need range of value for x. First, we need to create range of value for x. So we've been using 3. I think 3 has been occurring in our guesses. So let's say our s is going to range from -3 to 3. So this is a shorthand way of creating that range of data. By now you are familiar with that, I believe. So this is our x data. So what do we need to do now? We need to get our y, right? So what do we say? Normally we should say y is equal to what? What's the formula again? What's the function? We should say y is equal to x raised to power 3 minus 3 minus 5. Yes, that works. Some of you can use that approach. But as an addition, as a plus, I'm going to use another approach. We just created a vector that is the coefficient of the powers in that function. We just created that. So I'll be getting that. I'll be using that approach. But some of you can use the approach I just described. So I have that. So I can call a function called polyval. Polyval. So when I call polyval, I will pass in my value of p, which is the coefficient of the powers inside my function. So when I call p, when I pass in p, then I'm going to connect it to x. So that means I'm going to supply p and x. If I don't supply x, there is no way my y will have any meaning related to x. Then polyval requires 2 arguments, so p and okay. So y equals to polyval, open the parentheses. So what is going to the parentheses? The vector, which is the coefficient of the powers in my function, followed by x. So I'm linking my y to x. So I don't need to display the value. So I can now plot the normal way we used to plot. Okay? So when we want to plot, this is a 2-dimensional graph. So we say x, comma, y. So if you like, you can specify the thickness of your line. We've touched that before. So you can do that on your own. So we have made a plot. This is what it's looking like. So you can use y line. You know you can use y line for this, right? When you use y line, it's going to plot a line where y is equal to 0. Let me quickly do that. But what would I have wanted to do is just to go to my figure and edit 1 or 2 things, move my axis upward and get the result. But let me just use the y line. So this y line I'm creating is going to be a dashed line and it's going to be red in color. Oh, I didn't hold on. I hope it works. Wow, it works. But the normal practice is to hold on before doing that. Okay, so we now see where it crosses, right? Where the graph crosses y equals to 0, the line where y equals to 0. But we can't pick the value easily like that. We can put the grid on. So let's put grid on so that we are able to do evaluation better. Okay, the grid is here, but it's not sufficient enough. It's not sufficient. So let's go to axis properties. From axis properties, let the x and y minor grid to be checked. Okay. So conveniently, you can now see that it is above 2.2. If you want to estimate it, it's above 2.2. Can you see it? So it's moving towards that 2.279 stuff. If you look at it very well, where the graph crosses. So it's showing only one value. Yeah. The approach that we used before now, which is roots, already established that if you only have only one real root, other things are complex numbers. So it's not a wonder that when we plot graphically, it's only one of the roots that it is showing. Which is very close to the values that we have been obtaining before now. Okay. Just a summary before I leave for today. So we have seen different methods of finding roots. Possibly we might come back to the application to one of the chemical engineering questions that I posed when I started teaching you Matlab. So we have solved like two. The one that requires simultaneous equation, which is the material balance stuff, then the one that has to do with the Fourier law. Okay, so this is like reaction kinetics. So we might come back to it because it actually requires the knowledge of root finding. So that's why it's coming up here. But before I go, let me just make a summary on the techniques that we have looked at. So we look at the roots function, which is built in Matlab. So we said it is designed specifically for finding the roots of polynomial. Okay, and it does not require any guess, like we have seen. Then the F0 requires an initial guess, requires 1. And the better part of it is that it is applicable for polynomials and functions that are not polynomials. So that's the advantage to that. Then we have looked at the iterative methods. Today we are able to look at the Newton-Raph's method and the second method. Okay, so those one also, they require initial guesses, and they can only give you one root, unlike roots that we used, but that is for only polynomials anyways. Then all of those methods that require guesses, you could use the graphical technique to get a good guess, because you find a solution using those methods that require, those iterative methods that require guesses. Depends on the kind of guess that you provide. If you provide a guess that is far away, it's not likely that it's going to convert to a solution. So if you use graphical technique, it can help you to find a good guess. For example, when we are looking at that graph, even when we put on the grid, the minor and the major, it was just an estimate that we could get. But if you have an idea of what the value is, then using other methods that require guess can help you get a good result. So we'll be stopping here. So with time, if time permits, we'll go to the bisection method, which is bet length using conditionals along with it. And we might also solve this applicative example that involves you using root techniques. Thank you. Or do we have any question on what we have done? For what? Okay. We will give you everything necessary for exam purpose. Okay. We'll give you everything necessary for exam purpose. Any other? Well, I believe these classes should be impactful beyond grades. That's my own focus for anything I teach. It should be beyond I want to acquire grades. So if you understand what I'm teaching, marks will follow you. That's not, you cannot dispute that. So as you gain knowledge, a lot of things will follow you, including the peripheral, which is your grade that you are targeting at this time. Okay. Any other question? Okay, thank you.